Hi, this is Chris Surbeck with an environmental remediation lecture. This one is on in situ biological treatment technologies. In situ technologies are technologies conducted in place. So they are conducted where the groundwater is. This is opposite to groundwater pump and treat, which is a technology where groundwater is pumped via wells and treated above ground. So why use in situ technologies? Well, the main reason is because pump and treat technologies are not very efficient in removing massive contaminant. Also, using pump and treat takes a long time to really clean up the groundwater, and because it takes a long time, it also costs a lot of money. So some advantages of in situ treatment are that, well, now there's no groundwater to dispose of. You're not pumping it away from its place, it's kept in place, and so it's cleaned up where its location is. No need to dispose of treated groundwater. Another major one is the last one here in the PowerPoint, and it's that this is more of a passive system. There's no operation and maintenance necessary as much as in groundwater pump and treat. Now let's remember here that for all kinds of remediation technologies, there always has to be ongoing monitoring. Okay, so we always need to know the progress of the remediation, if we're really controlling the groundwater flow, if the contaminants aren't migrating farther away, if there's a false sense of security thinking that the contaminants are going away and really not. So that's partly what rebound is. And we also need to monitor media that are exposing people. So air and groundwater, people can be exposed to them. That always needs to be monitored during any type of remediation technology. So what are some of the technologies we'll talk about here? The three primary ones are bioremediation, then phytoremediation, and natural attenuation. So we're talking here primarily of technologies that are biological. Let's look at in situ bioremediation. Let's look at a jargon type of definition here. So bioremediation here, and specifically biostimulation, is an engineered system that stimulates microbial degradation of contaminants in the subsurface. So what does this really mean without the jargon? Okay, we're creating an environment in the subsurface that basically make bacteria happy, so they eat or somehow destroy chemicals that we don't want. So these are two definitions of biostimulation, basically making the bacteria happy, doing something to make them happy and want to basically eat the contaminants. Another definition here, biodegradation, is a more general term. It's basically the destruction of a contaminant by bacteria. So that's kind of an overarching overall definition. Another definition here, bioaugmentation. This is adding bacteria to the subsurface, and these bacteria are not naturally present. Okay, and so this is what a lot of people think bioremediation is, but for the most part is really biostimulation, not bioaugmentation. Bioaugmentation should be used with caution because sometimes putting in bacteria that aren't normally present in the subsurface is just bad for the bacteria. They'll die and not do what we want them to do. Okay, this is a list of contaminants that are amenable to some kind of biological treatment, so you can read these here and pause the video if you need to. Let me just point out a few acronyms here. BTEX, this is the abbreviation for benzene, toluene, ethylbenzene, and xylenes combined. Also another abbreviation here, MTBE, this is methyl tert butyl ether. It was an additive to gasoline primarily in the 90s. Okay, and then some of the other ones, if you've been studying environmental remediation, you may be familiar with these already. Okay, a few more definitions. Metabolic degradation. This happens when bacteria basically consume the contaminant. Basically, is the equivalent of us people eating food. Okay, bacteria can metabolize contaminants. Another one here, co-metabolic degradation. This is when a contaminant is degraded only in the presence of another. For example, chlorinated solvents, PCE and TCE, that's tetrachloroethylene and trichloroethylene, they are not directly metabolized. They usually are only metabolized in the presence of something else. What we see a lot is addition of methane into the subsurface, and then bacteria degrade the methane, and that in turn degrades the PCE and the TCE. So that's co-metabolic degradation. It's sort of an indirect degradation of the chemicals through another chemical, in the example here, methane. Aerobic bioremediation and anaerobic bioremediation. This is the difference between remediation in the presence of oxygen, aerobic, and not in the presence of oxygen, anaerobic. Also here, electron transfers and electron acceptors. This is referring to reduction-oxidation reactions. Here's a list of electron acceptors. So if you are familiar with the chemistry of redox reactions or reduction-oxidation reactions, these are chemicals that get reduced in an electron transfer process. In aerobic respiration and basically aerobic bioremediation, oxygen is reduced, and in anaerobic bioremediation, these other chemicals here are reduced. Okay, so how does all this happen? For example, how do we stimulate aerobic biodegradation? Well, add oxygen. Okay, how do you do that? Inject air or inject oxygen as a gas or in some other way. This picture here on the right shows an in-well sock, okay, by a company called Regenesis, and so there's a substance, a powdered substance in here that can be installed inside the well, and as the groundwater moves through this powdered substance, the powdered substance releases oxygen, and that way it releases oxygen to bacteria existing in that soil and groundwater. Bacteria are happy, they can undergo respiration and at the same time metabolize contaminants. So this is one way that aerobic bioremediation can be done. Little note here on the bottom, what if it's in a cold place like Alaska? I think we all know that that cold temperatures are not good for microbial and chemical reactions. Well, maybe you can add some heat on top of all that to speed things up. A simple system here for implementing bioremediation is called bioventing. This is generally in the vadose zone of the soil, so the unsaturated zone, not the groundwater. And this is about circulating air through the soils to stimulate biodegradation. If you inject air into the soil, that air contains 21% oxygen, and so it will biostimulate local bacteria. So the purpose of bioventing is not to strip VOCs. If you're familiar with soil vapor extraction as a remediation technology, that is a technology for stripping VOCs, removing VOCs from the soil and into an airstream. That's not the purpose of bioventing, although technology-wise it's done in a similar way. Let's look at how this can be done. Here's bioventing. Okay, it says here when soil vapor extraction promotes biostimulation. Again, the purpose is not to remove contaminants through an airstream, but to have a similar technology just to promote biostimulation. Usually what that means is lower airflows, just enough airflow to promote the growth of bacteria. Can also do bioventing with nutrients, so injecting here, in this case, ammonia, oxygen, and then having that gas pass through the contaminated soil and then collecting that air through soil vapor extraction. Let's look at anaerobic biodegradation. The point here is to have biodegradation in the absence of oxygen. So again, there are different nutrients and different patented technologies that can be done for this, and so these are some examples here. In fact, some things are not even patented. Certain sugars and molasses can do the same thing. Let's look at another biologically based remediation technology, and this one's called phytoremediation. This is the use of plants to remediate soil. So different kinds of plants, we're not going to go into the particular ones here, but different kinds of plants can degrade or collect contaminants. If the groundwater is shallow enough, close enough to the soil surface, or the roots can get to it, then phytoremediation can happen. It says here it can be non-destructive or some destructive techniques. The destructive here means destructive to the chemical. We know that a destructive technique will break down the chemical molecule. A non-destructive technique will simply pass that molecule from a place where it's not desired to another place where it then can be disposed of. Here are some different concepts, and you can pause the video to look at the colored key here on the bottom and look at these 6 different scenarios that can cause plants to remediate soil. Let's look at number 3 here, monitored natural attenuation. This is a technique and not a technology. This is a technique in which no physical action is done to remediate, however, there is monitoring. Okay, let's look at the 3 words here, monitored natural attenuation. Monitored, okay, so a lot of collecting samples and continuously going to the site to examine the site. Natural attenuation, this is letting nature take its course to attenuate the concentrations of chemicals. You can see here all the physical, chemical, and biological processes that can happen naturally. Okay, so how do we know that monitored natural attenuation is happening and chemicals are degrading naturally in the soil and in the groundwater? These are the ways, okay, listed here in this slide. If over time from collecting samples we see that the contaminant concentrations are decreasing, then that's evidence that monitored natural attenuation is happening. Another way of monitoring is checking the bacterial activity, checking other gases that occur naturally in the soil, and if they're changing over time, which might indicate some chemical redox reactions happening that are helping the transformation and the attenuation of those chemicals. This concludes the lecture on in situ biological treatment for environmental remediation. The 3 main items talked about here were number 1, bioremediation, number 2, phytoremediation, and number 3, monitored natural attenuation.